Okay, so we're going to jump from chapter 2 to chapter 8, just because it's a natural flow of information, where we talked about the nucleus and the Rutherford experiment, how we determined that the nucleus is in the center of the atom. We're also going to talk about the electrons in the atom. We're going to talk about electromagnetic radiation first as a prelude to our discussion of quantum mechanics and how it impacts what we now know to be orbitals around the nucleus or within the domain of the nucleus. We'll talk a little bit about quantum theory of hydrogen and interpreting representation of orbitals of hydrogen through various means. We'll also talk about electron spin, the Pauli exclusion principle, so on and so forth. And then we'll bring our model of quantum mechanics to multi-electron atoms and electron configurations, and finally how electron configurations fit into the periodic table. So inside the atom, in the last chapter, we learned that the nucleus through the Rutherford experiment occupies a very small volume relative to the total volume of the atom. And so we got to ask ourselves, well, what's in all that empty space? Well, we know electrons are in empty space. So how are the electrons arranged inside that atom? How do they occupy all that domain, and in what fashion? And because electrons they all have the same charge, being negative, how do they arrange around that nucleus so that they're not bumping into each other and they have their own domains? So to answer that question, we have to first start with electromagnetic radiation. So before we can begin to talk about quantum mechanics and orbitals and things like that, we have to talk about electromagnetic radiation as a prelude to what we're going to discuss in electron configurations. So looking at electromagnetic radiation, the definition, it's a form of transmission of energy, and let's not forget magnetic fields, as they are propagated through mutually orthogonal waves through empty space. Or it could be a medium like water or glass or a solid, so on and so forth, that we can talk about, and it's affected or impacted by that medium. And so looking at the electromagnetic spectrum, we see the electro part and the yellow, representing the yellow sinusoidal configuration. You'll notice a direction of that propagation. You also see a mutually perpendicular, shown in purple there, magnetic field. And the point the distance between identical points in a wave repeat is called lambda. We'll get into that. And so know that waves transmit energy. They do. And higher frequency waves are much higher energy, and we'll talk about how that works through Planck's constant. Some examples of radio waves, we'll show you another graphic in just a minute, but we can go from very, very long waves like radio waves to extremely small waves with high energy. So low energy and high energy, long wavelengths, very short wavelengths, and we'll show you a representation of the properties of waves. We have length. We have to look at the length of a wave, and that's going to be represented with the Greek letter lambda. And lambda, of course, describes the distance between identical points on successive waves. And a wave, any wave, will have an amplitude, which is a vertical distance from the midline of that vector of the wave through the peaks and troughs of that wave. That would be the amplitude. And then we talk about frequency, of course, how many times it occurs per second. And so you might remember seconds as being the psi unit that we use to measure time. And so we use the Greek letter nu, pronounced nu. It looks like a V in our alphabet, but it's called nu. That's the number of waves that pass through a particular point in space in 1 second. That's right, in 1 second. And so we'll represent that as reciprocal seconds, or if you hear hertz, hertz means times per second. And speed, of course, if you might relate it to your own world. If you're in a car and you're traveling 60 miles per hour, the miles is the distance bit, and the hour is the unit time. Okay, well, we can also relate that to the electromagnetic or a microcosm. We can say that speed, which is generally represented with the U, is equal to lambda times nu. And so that we're saying that the speed of something is just equal to the distance per unit time, or yeah, unit length per time. Okay, and so we talked about the electromagnetic wave as being sinusoidal and have a perpendicular magnetic moment. But what's really important that you get your head around, in chemistry, we're talking about three-dimensional entities, atoms. And interestingly enough, we're also relating the quantum mechanics of an atom to the electromagnetic spectrum through looking at these three-dimensional vector, the XYZ axis. And so in one axis, we have the direction of the wave, the propagation of the wave. And then we have the electric field associated with that wave and its perpendicular magnetic moment. And so what I want to look at now is the frequency, very low frequency, and how that relates to wavelength, lambda. So if we have a low frequency, fewer number of times per second, we can see that the wavelength is longer. And so this tells us that we look it over, well, it'll eventually tell you that they're inversely proportional. So low frequency versus high frequency. And so something of higher frequency, the wave travels through the same point in space at a greater number of times per second. And in doing so, the wavelengths are shorter. And so we can see that there's an inverse relationship between wavelength and frequency. And so we have a proportionality now. We say that nu is inversely proportional to lambda, or we can say that frequency is inversely proportional to wavelength. So wavelength and frequencies are inversely proportional. So frequency, wavelength, and speed of electromagnetic radiation. Okay, so we're going to build a model here. I want to make sure our units are, we're using common units. So frequency nu is the number of times it occurs per unit second, per time. The wavelength is distance, lambda, and don't forget we use the meter in the SI units for measuring distance. And so here, with respect to distance, meter, we can have 10 to the minus 2, so that's 100, 1/100th of the distance of a meter. Then we have 10 to the minus 6, 10 to the minus 9th, 10th, and 12th, so on and so forth. So we can have very large or extremely small wavelengths. Velocity, we'll talk about electromagnetic radiation. The speed of light is 3 times 10 to the 8th meters per second, or it's a number very close to 3. We'll just use 3. Okay, so 3 times 10 to the 8th meters per second. That's a long distance per unit time, that's for sure. So the speed of light, c, we'll represent c, is equal to lambda times nu. And with that simple arithmetic equality, we can, of course, get relationships for lambda as speed of light divided by nu, or we could say that nu is equal to the speed of light divided by lambda. Okay, and we're going to use these when we do some derivations coming up for various properties of electromagnetic radiation. So in 1873, Maxwell proposed that visible light consists of electromagnetic waves that we have just discussed. And so the radiation, of course, it transmits energy in the form of electromagnetic waves. And so all electromagnetic radiation follows this equation where the speed of light is equal to lambda times nu. And notice that C is used for the speed of electromagnetic radiation. And so the energy, as it relates to electromagnetic radiation, we said that earlier that it transmits energy. And since light is a wave, how can we calculate its energy? Well, we can say then that energy is proportional to frequency. Okay, so when we invoke, and this little red alpha, we use the Greek letter alpha to discuss proportionality. And so if we say that energy is proportional to the frequency, then if you invoke, when you go to an equality, you have to invoke a constant. Okay, so anytime you go from a proportionality to an equality, you must invoke a constant. And so Planck's constant for energy is equal to Planck's constant times nu. And Planck's constant is 6.6 times 10 to the minus 34th joules seconds. And energy, of course, is in joules. And so what are the units for nu? Reciprocal seconds. And so our seconds will cancel out. And what are we left with? Joules. And so we can do our substitution for nu. We can say that energy is equal to Planck's constant times the quantity of speed of light divided by wavelength. Here's our spectrum of electromagnetic radiation. Let's look first at frequency at the top. This is the number of times it occurs per second. 10 to the 24th. That's a big number. 10 to the 20, it's unimaginable. 10 to the 24th. It's going through a point in space 10 to the 24th time every second. And then you can see that these become decreasing, I should say, down to 10 to the 4th, which is a very, very large wave. 10 to the 4th meters, remember we're talking about meters here, frequency, excuse me. This is 10,000 times per second, and this would be a million times per second, so on and so forth. Coming down here now to wavelength, we can see that wavelengths go from very, very, very small to very, very large. Okay, 10 to the 4th, that's 10,000 meters per 10,000 meters, which is a long distance. In the visible spectrum, we see that light, lambda, has a wavelength of 390. Of course, over to the red spectrum, which is ends out at around 760 nanometers. And so what we see on this planet, or what we see around us, is in this tiny little window in the entire electromagnetic spectrum. And you can see that there's an inverse relationship between wavelength and frequency. So to give you some examples in real life, we use radio waves to broadcast radio and television signals. Okay, we use microwaves, which are a little bit shorter and greater frequency for cooking. When you have a radiator, that's transmitting infrared energy, electromagnetic energy. We have visible light, which makes things visible to us so that we can see. We have UV light, which you can see what's happening to the frequency as we go from left to right. It's getting greater and greater, isn't it? We get to X-rays, which we have very high frequency. And we can, when an X-ray bounces off an object, we can see that, and that would be the structure of the bone. It goes straight through the soft tissues and bounces off the hard bones. So anyway, X-rays are very high energy, potentially damaging to the cells, so you don't want to get too much radiation. And then gamma rays, of course, are the highest energy and the greatest frequency. And they're used in medicine for killing cancer cells. So if you're going to talk about radiation for treating cancer, you're talking about gamma rays, and they can be extremely harmful to all cells, both cancer cells and surrounding cells. So let's talk about phase and overlap. When two sinusoidal waves are of the same frequency and the same wavelength, here and here, then when we add those waves together, we get a doubling of the amplitude and the trough and the peaks. Okay, and because of the same frequency, they've maintained their given frequency when they overlap. So what do? It just adds an amplitude. Okay, when they're in phase with each other. You can see by this the blue circle here that these guys are in phase and they're additive. Okay, so the wave functions are in phase and additive, so we get an increase in amplitude. When the waves are out of phase, when this part of the wave is going up and down, this part is going down and then up. When we add these two waves together, we get the null set. Okay, so there is zero overlap, and so they cancel each other out. This becomes important. This part over here becomes important when we start talking about electrons in their orbitals. So wave functions that are out of phase cancel each other. Okay, and in quantum mechanics that becomes important when we talk about antibonding orbitals and things like that. Looking at the emission spectra, light is composed of various colors as we've discussed. And emission spectra are represented as lines of radiation emitted by substances or elements. So this is a big deal. Matter emits light. That's what a concept, huh? Where does all that light come from? It comes from matter. And so that's a big epiphany. Where does light come from? It comes from matter. And so every element has a unique emission spectrum. It's a good qualitative test as it turns out. But why is that? Why do some elements, why do they have unique emissions? Well, let's talk about emission spectra and what they are. This is at figure 8.9 in your book. It's the atomic or line spectrum of helium. And so the experiment, we have a cathode and an anode, and we have a tube filled with helium, and we're sending electric charge through that from the cathode to the anode, and that takes helium from a ground state into an excited state, and when it goes back down to the ground state, it emits light or photons, and we'll send that through a slit, and then send that plane polarized light or planar light through a prism. And the prism, of course, will take the wavelengths. The longer the distance, the shorter the distance, will have relationships between where they occur in their frequency and in their wavelength. Okay, and so that'd be a photographic film plate. These lines over here are called emission spectral lines, and you can see that they're basically quantized, and we'll talk about what that means. But each element, the important part is each element has its own emission spectrum. So helium gas, as I said in the tube, is a closed system, and that's the distance in frequencies, distinct frequencies for helium. And so hydrogen would have a different emission spectrum than helium, which would have a different emission spectrum than the rest of the elements in the periodic table. So looking at sources of light emission, of course we had our helium, and we have neon, so on and so forth. But this is pretty interesting. There's hydrogen on the left, neon on the next to that. If we have a lithium rod or lithium in the rod, when we heat it in a flame, the electrons go from a ground state to an excited state, and they precess back down. And in the visible spectrum, we see that as red. Sodium, you're going to see yellow. And don't forget, these are the lower energy. And finally, we have potassium in the higher energy portion of the visible light spectrum. And so you can see that metals give off different colors based on the frequency of their emission spectrum. And so again, this is the emission spectra. Frequencies are specific and unique to each element. Max Planck in 1900. He's a German physicist. He observed that solids, when heated at various temperatures, emit energy in discrete quantities, or quanta, and that's important. So when you heat an element, it'll emit energy in quantized packets. And so the emission spectra are excellent qualitative means for determining the identity of an element. And also, you might want to remember that emission spectra were the first evidence that they didn't know it at the time, but the first evidence of quantized quantized distances, quantized emissions of a photon, and also at the atomic level for the structure of the atom. So here's a bewildering slide, but a lot of information there. These are all the group 1s, sodium, lithium, potassium, not all of them, some of them, calcium in group 2s. Here we have transition metals, so on and so forth, and then the noble gases. But the big point is that each of these elements has a different emission spectrum, and so it's a good qualitative test. So along comes Max Planck at the turn of the century of 1900, and his work ultimately evolved into what we now call quantum theory, and looking at discrete emissions of light. And so let's understand first of all that an object that absorbs all radiation falling on it at all wavelengths is called a black body. Okay, just for definition purposes. So something that absorbs all light at all wavelengths. Well, when a black body is at a uniform temperature, okay, the same temperature, isothermal, its emission spectrum of light has a characteristic frequency, okay, and this is very important. And the frequency distribution is temperature dependent. So if temperature dependent, how do we make sense of that? The higher the temperature, you would think the more the energy, right? Okay, well, that's true. So the emission of light from a black body, it's called black body radiation, okay? And we talked about emission spectra being quantized. And so classical physics could not provide a complete explanation of all light emissions by heated bodies or black body radiation. Okay, and so the problem was that classical theory could not explain the observations in the UV portion of the spectrum. And so in science, you might recall, if a theory does not explain all of the experimental observations, then the theory must be changed or modified to fit all that data. Okay, so you can't cherry pick the bits that you like. You have to take into consideration all scientific observations to support a theory, or maybe change a theory. And this is what happened. This was a change from Newtonian, the evolution, if you would, of quantum theory based on the failure of Newtonian physics. And so Max Planck's work in 1900, he looked at wavelength as a function of intensity, or intensity as a function of wavelength. And we're in the visible spectrum here, you can see there. And so at temperature of 5,000 Kelvin, we have a certain intensity, lower intensity. And at 7,000 Kelvin, we had a higher intensity, as you might expect, as a function of pure quantum amount of heat. And so classic physics fits very nicely for intensities at higher wavelengths up in here, but it fails at lower wavelengths. And so became known as the ultraviolet catastrophe, from which quantum mechanics was born. And so in classical theory, look at these dotted lines, you would see that the intensity should be infinite. And we see limitations here. We see discontinuous observations, but in classical theory, at much higher temperatures, the UV spectrum it fails. And so you can see where classical physics fails as a function of intensity and wavelength. So given that, classical theory predicts that intensity of emitted radiation would increase indefinitely, as you see here, okay? But it doesn't. Classical theory also places no limitations on the amount of energy of a system or the amount of energy a system may possess. Well, we know that can't be true, and where the failure occurs is in the UV spectrum at very high temperatures. Okay, the fact is that black body emission spectrum intensity does not increase indefinitely. Okay, and that's where classical physics, in simplified terms, that's where classical physics fails. So we had to develop a new model, if you would, to describe the observations. So Max Planck proposed that energy, like matter, is discontinuous. It is finite. Okay, and so matter, being finite, cannot emit energy that is infinite. It too is finite. Okay, and so changes in energy occur in limited packets or quanta. Okay, so now we're going to enter a new theory because of the failure of classical Newtonian mechanics at the atomic level for emission of radiation. So here comes quantum mechanics, and quantum mechanics enables us to predict and understand the critical role that electrons play in chemistry in general, and more specifically in chemical bonding, which is where ultimately where we're headed. And so through quantum mechanics, we can describe how many electrons are in a particular atom. Okay, so how many electrons are in a particular atom through QM. We can also describe through quantum mechanics what energy individual electrons possess. And when you look at the periodic table, you can see energies as quanta. That would be the horizontal rows in the periodic table. And we can also, through quantum mechanics, describe where electrons can be found. So looking at this package of quantum mechanics and what it can do for us at the atomic level, okay, it can tell us, now we can begin to describe what fills all that space around the nucleus and how the size of the nucleus impacts the size of the atom and where the electrons live relative to that nucleus and energy levels that each of them has. So looking at classical versus the quantum world, in classical mechanics, we can say that in everyday life, quantum effects you can ignore them. They're not impacting what you in this three-dimensional world of ours actually see and feel. That's because Planck's constant is so extremely small. But in the quantum world, at the atomic size, at the atomic level, these scales, quantum effects are dominant and must be considered. So the laws of nature developed without the consideration of quantum mechanics just don't work. Okay, so we have to rely on quantum mechanics to understand the physics of or the exchange of electrons between atoms in chemical bonding. So let's look at the photoelectric effect. What is that? Well, in 1888, a guy named Hertz, you might remember Hertz, he observed that light striking the surface of a certain metal causes ejection of electrons. Okay, and we can say that the number of electrons ejected from the metal surface depends on the intensity of the light that is being ejected, the incident light. Okay, and the kinetic energies of the ejected electrons depend on the frequency of the light. Okay, so the energies now of the electrons are a function of frequency. Okay, and so Einstein, with all of his work, and he had just a large body of work in science, he proposed that electromagnetic radiation of a photon has both particle-like and wave-like properties. And so matter at the atomic level has a duality of particle-like behavior and wave-like properties. And where the energy of a photon is equal to Planck's constant times nu. Okay, so we're going to use that as forward. And so looking at the photoelectric effect that we described earlier, it demonstrates that electrons have quantized energy levels. So here's our incident light, h nu, and it strikes a surface, a metal surface in an evacuated chamber. And when that electron is emitted, okay, it goes through a grid, and when it goes through a grid, it creates a current. Okay, so the electron is being emitted, and a current is being generated as the electron passes through that grid. And so we call this the photoelectric current, and these are various intensities. And you can see at any given frequency, it is constant. But the intensity of the current increases in quantized steps. Okay, so that's the photoelectric effect. So energy intensity of a current is quantized. Okay, and so we can measure the voltage, and we can see here that the voltage, as measured across that current, we can see that the voltage is proportional to frequency. So we have frequency on the x-axis and voltage on the y-axis. We can see a linear relationship between voltage and the frequency. We say that they're proportional. So early attempts to understand atomic emission spectra and using all of the work of Einstein, so on and so forth, Bohr, a gentleman named Bohr, he was one of the first to describe what the atom was, based on all the observations that we've seen so far. And so Bohr's model of the atom said that the electron moves around the nucleus with a speed in one of a fixed set of circular orbits. Okay, so he was a little bit off on that one. As long as the electron remains in a given orbit, its energy is constant. So we know that to be true. No energy is emitted. Thus, each orbit is characterized by a fixed radius and by a fixed energy. Well, the electron's angular momentum, we'll call L, or let's just call it L, is a integer multiple where n is some energy is equal to Planck's constant divided by 2 pi, with n being some whole number integer 1 through ad nauseum. And so an atom emits energy as a photon when the energy falls from a higher energy level to a lower energy level. Okay. And so radiant energy, when an atom is in an excited state due to the external influence of its valence electrons, it can go from lower energy. When something is heated, the outer electrons, the electrons furthest from the nucleus, can be promoted to higher energy levels. So they go from a ground state to an excited state based on external influences, typically heat or intensity of light. So radiant energy is in an atom is in the form of a photon, and a photon is emitted in quantized transitions, as we saw in the photoelectric effect. So when the electron moves from a higher energy to a lower energy, it releases energy in packets. It's the way the model that I would use is if you take a stairwell, each step is a quanta, is a step going from higher to lower, lower to higher. And the rail on a stairwell could represent classical mechanics, where the steps kind of represent, as a model, the quantum mechanics. And so a photon is a subatomic particle that demonstrates particle-like and wave-like properties based on some of the work that Einstein did. And so recall that energy of a photon is equal to h nu. So then we can now Bohr's model. So this little red dot in the middle would be your nucleus. And this is the planetary model for hydrogen, And so where n equals 1, that would be that energy level right there. Okay. And energy level 2 would be a quantized, but a definite distance. Okay, so we have energy level 1, energy level 2, energy level 3, and so on and so forth, energy level 4 out the outer extremes. Okay, well, n goes up through from 1 to 7, as we'll see in the periodic table, and there are 7 quantum levels in matter. And so n goes 1 through 7. Only n equals 1 through 4 are shown in this diagram. So this is the Bohr model of an atom, of the hydrogen atom. Okay, and so when an electron is promoted, when the hydrogen atom electron energy is promoted, it can go from the first energy level to the second, as seen here, or excuse me, the second to the third, or maybe the second to the fourth, so on and so forth. But when it's in a very, very high unstable state, and the electron will fall back down in quantized fashions to a lower energy level. Okay, so when the external source of energy is removed, those energies will precess back down to lower energy levels. Okay, when that happens, light is emitted. Okay, and so some of this light is in the visible spectrum as well. And so the absorption of energy, the black arrows, indicate the excitation of an electron. Okay, going from the first orbital to up through and to including the 7th quantum level. And so emission of energy is the colored arrows as represented here. Okay, so when does the emission occur? When the energy is when the source of energy that put it into an excited state is removed, then the electrons will precess back down to lower energy levels. And so that energy can be described as the negative quantity of the Rydberg constant divided by the energy level squared. Okay, and so the Rydberg constant is, you don't have to remember this number, 2.2 basically times 10 to the minus 8th joules. All right, so the Bohr's planetary model of the atom, this is back in 1913, a little more than 100 years ago. The Bohr was the first one to come out and propose the structure of the atom. So when the electron goes from N1 to N2 to N3, when it precesses back down to a lower energy level, a photon is emitted. And so electrons can only have specific quantized energy values. And that's very important, very, very important. Light is emitted as the electron moves from one energy level to a lower energy level. So going from a higher to a lower, light is emitted in the form of a photon. And the energy is energy level function dependent, and it's equal to the negative quantity of Rydberg's constant times the reciprocal of the energy level squared. And as this number down here gets bigger, you can see that the energy is going to get smaller. So the principal quantum numbers are 1 through 7, and the Rydberg constant again is 2.2, basically 2.18 times 10 to the minus 8th joules. And so the Bohr's planetary model of the atom, this is back in 1913, a little more than 100 years ago. The Bohr was the first one to come out and propose the structure of the atom. So when the electron goes from N1 to N2 to N3, when it precesses back down to a lower energy level, a photon is emitted. And so electrons can only have specific quantized energy values. And that's very important, very, very important. Light is emitted as the electron moves from one energy level to a lower energy level. So going from a higher to a lower, light is emitted in the form of a photon. And the energy is energy level function dependent, and it's equal to the negative quantity of Rydberg's constant times the reciprocal of the energy level squared. And as this number down here gets bigger, you can see that the energy is going to get smaller. So the principal quantum numbers are 1 through 7, And the Rydberg constant, again, is 2.2, basically 2.18 times 10 to the minus 8 joules. Okay, so what is a photon? Well, a photon is a type of elementary subatomic particle. Light is made up of photons, obviously, if it's something we can see in the emission spectrum, visible spectrum, as well as other parts of the electromagnetic spectrum. But light is made up of photons, and electrons contain photons, and photons are basically quantas of energy. And photons have a mass of 0 and travel with the speed. Here we have a diagram of energy in the y-axis, going up in the model anyway through infinity. And we have, so it's called ionization or promotion of an electron to higher energy levels. And then we have this horizontal line, which would represent energy levels 1, the first quantum level, which is that which is closest to the nucleus. The second quantum level is a distance further, third, fourth, and fifth. And you can see that the steps are getting, as you go from 1 to 2, the distance in energy is much greater than 2 to 3, and is much greater than it is from 3 to 4, so on and so forth. And so we can say that if the electron of a hydrogen atom absorbs this amount of energy in joules or more, it is removed from the quantum orbital framework, and ionization of the hydrogen atom occurs. In other words, if you just completely take the electron away from the atom, leaving behind a bare proton. And in doing so, the system will absorb energy. So when energy is emitted, let's say the electron stays within the framework, the quantum framework, energy is emitted when the electron falls from higher numbered orbitals to the orbital n equals 1. When that happens, it's the ultraviolet spectrum, which produces spectral lines called the Lyman series, okay, which is not represented here. Well, it is right here. So this is the Lyman series, where it goes from higher energy levels down to energy level 1, okay, and that's in the UV spectrum, which we do not visibly see. And electron transitions to the energy level quantum shell equals 2. We see emission lines in the Balmer series. Go to figure 8.10, I think, in your book. So the 3 lines are shown here in color to represent the visible spectrum. So this is called, again, the Balmer series. And you can see that we go from UV radiation, or I guess it should be higher energy, to lower energy, and the photons that are emitted are quantized as a function of energy level. And so the transitions to n equals 3, so higher energy down to 3. Okay, so the change in energy is final minus initial, because energy is a state function. So the change in energy is the energy minus final minus initial, which is equal to the square of the quantum level in the denominator. So it's the Rydberg constant divided by the square of the energy level for the electron. And so we can see that all this just is equal to h nu, which is equal to Planck's constant times, again, the speed of light divided by lambda. Don't get too involved with this. What I really, the math, don't worry about all this. What I really want you to understand is that there's transitions from higher energy levels to lower energy levels, and they emit different kinds of light. The Lyman series is the UV spectrum. The Balmer series is the visible spectrum, and that is where it goes down to the energy level of the second quantum level. In this example, let's look at 2 different things. Let's say we have an electron in the excited state, and as it precesses back down, it emits light, and so we get what we call an emission spectrum as it goes through the prism. Or if we have a source of white light here, and it goes through a sample, and then is split into a beam or put into through a rectangular slot, makes a beam, and it goes to the prism. Then we get an absorption spectra. But you can see that the black lines in the absorption spectra line up exactly with the emission lines in the emission spectrum. So both give you the same information. It's just whether you're absorbing or emitting. But what you do see, and I want you to pay particular notice, is that you have these exact frequencies, exact frequencies. It's not a continuous, it's discontinuous, it's quantized in both in both experiments. Well, there's two ideas leading to the new quantum mechanics. There's the wave-particle duality, and we won't go through all the history or the math of that. But Einstein suggested that there were particle-like properties of light, and they could explain the photoelectric effect that we talk about. And de Broglie, around the same time, suggested that diffraction patterns that he observed in his experiments looked wave-like. And so depends on how you're looking at it, but it can be either a particle or a wave depending on which experiment you're looking at. Okay, so let's look at the wave-particle duality. It's a matter of perspective, okay, where we know that energy, E, is equal to Planck's constant times nu. So that relates energy to frequency, okay, this equation, just by that constant, Planck's constant, okay. Einstein's work also showed that energy is equal to the mass times the speed of light squared. And so that relates mass and energy. Okay, so this one up here relates frequency to energy, and this one here relates mass to energy. And there's the duality of the energy of a particle of light, mass or frequency. And so then by substitution we can say that, and don't get lost in the math here, guys, just follow along. H nu is equal to mc squared. And so we're going to do a little razzle-dazzle math where we talk later on. But anyway, let's go down here. Wave-like, which is what, meters distance, lambda, is equal to Planck's constant divided by the momentum of the photon. And through substitution, we can say that it's mass-like. And through this one equation, we can say that we have wave-like equalities and mass-like equalities. Well, don't get lost in that. Just kind of follow along as we're going. So the speed of light, remember where the speed of light is equal to lambda times nu, then again, we get frequency and distance. So the uncertainty principle states that in quantum mechanics, the uncertainty says that the position of a particle and its momentum, p, cannot be known simultaneously, all right? And so the Heisenberg uncertainty principle states that the more precisely the position of some particle is determined, we're at the atomic level here, the less precisely its momentum can be known, and vice versa. And so that brings us to what we call wave mechanics, which becomes important when we talk about molecular orbital theory later on. But again, try to stay with the concepts. You can think of an orbital as a standing three-dimensional wave, but this is a two-dimensional representation. A node in this model on the left is a point along a standing wave that has minimum zero amplitude. A node is a point of separation between two orbitals. So orbitals are not intersecting, what this says, what this wave mechanics says, that orbitals do not intersect. All right, and there's zero electron density where they don't intersect. And so electron as a matter wave, when a standing wave is a two-dimensional circular model as shown here, okay, the numbers n of the standing waves and nodes have to be whole integers in order to continuously overlap. You can't be fractional. So we're getting back into our quantum mechanics here. And so this is a standing wave in phase. and this is standing waves out of phase in the wave matter model. So when the number of standing waves is not a whole energy, then continuous overlap is not possible. Okay, so it has to be a whole number basically. So what we're saying is that the energy levels of electrons have to be in discrete energy levels away from the nucleus. Okay, and so they're not discontinuous, if you say. And so standing waves and quantum particles and wave functions. All right, well, don't get lost in this one either. But what is important, I want you to focus on this little kind of a weird Y-looking thing. It's called psi. And this is Schrodinger with some serious math chops. But anyway, psi is a wave function. All right. And it should correspond to a standing wave within the probability boundary of a system being described. Okay, and so if you take a function and you square it, you get a probability, and we're talking about 3 dimensions, so it's going to be a 3-dimensional boundary of the system that you're describing. And so for each electron in the atom, the psi function identifies its energy level, the shape of the orbital, the orientation of that orbital, and the spin, positive or negative, of that of the electron. And so here is Schrodinger's equation, where each electron is a function of energy, it's a function of shape, it's a function of orientation, and because only two electrons can occupy a given orbital, and they're like charge, then they're going to be chasing each other around in that orbital far away from each other as possible. And so that would be the spin of either 1/2 or plus 1/2 or minus 1/2. So that would be the Schrodinger wave equation. And so quantum numbers and electron orbitals. So if we look at the Schrodinger wave equation for each electron, this is important. Now we're beginning to describe what the spatial domains are of an electron around a nucleus are in the entire atom. Okay, and Schrodinger's wave equation says energy, shape, orientation, and spin. The principal quantum number is n, and if you look at the periodic table, it goes 1 through 7. The top of the periodic table, hydrogen and helium are in 1. You go down below that, that's energy level 2, 3, and as you progress down the periodic table, the atoms are getting bigger and bigger and bigger. And so you're adding multiple layers of energy. So that's the principal quantum number n. That's the energy level. The angular momentum quantum number is L. Okay, and I'm going to get into more detail here. But L describes the type of orbital. Is it an s orbital? L equals 0. If it's a p orbital, L equals 1. If it's a d orbital, L equals 2. And f orbital, L equals 3. So there's only 4 there that you need to know. S, p, d, and f. And this is the angular momentum number, quantum number. Angular momentum quantum number describes the type of orbital that it is. S, p, d, or f. So that's the orbital shape. And the type of orbital is determined by its shape. And we'll talk more about shapes in just a little bit. The magnetic quantum number, m sub L, describes orientation. So the momentum quantum number describes the shape. The magnetic quantum number describes the orientation, m sub L. And think of m sub L as a number line. If this were 0 on a number line, you could go to the left and it'd be negative. You could go to the right and it'd be positive. And they're always going to be in, so if you only have one orbital, like the s orbital, its magnetic quantum number has to be 0. If you have a p orbital, as we will talk about in a little while, you have 3 p orbitals, then the magnetic quantum number would start at 0. Because you have 3, you'd have a -1 and a +1. In magnetic quantum numbers, the value, the sign is negative and positive, means nothing in terms of mathematics. It's just a designator around 0. Okay, it doesn't have does not have numeric value. It's a label. And then finally, that's the orbital orientation. And then finally, we have the spin quantum number S, and we can have a plus 1/2 or a minus 1/2. An orbital can only be the maximum number of electrons an orbital can have is 2. It can have 1 electron or 2 electrons, but that is all. That is the upper limit. It cannot have more than 2 electrons. And because electrons are of like charge, then they're going to be on opposite ends of each of those orbitals or in different domains of that orbital and not interfering with each other. And that would be called electron spin. And so again, Schrodinger's equation gives a very nice description of energy level, orbital shape, the orbital's orientation, and the electron spin. So that leads us to electron energy levels. So there are 7 quantum levels for electrons in the atom. So look at the periodic table in the front of your book, open that cover up, and at the very upper left-hand corner of the periodic table, there's hydrogen. And you'll see numbers 1 through 7 going down. In quantum level n equals 1, an electron is closest to the nucleus. You cannot get any closer to the nucleus than n equals 1. And it's spherical. It is a sphere like a ball. That would be the 1s orbital. The most stable state for an electron, for an atom, with all of its electrons occupying their respective lowest energy levels, we call that the ground state. Okay, that's where no external forces or interactions. There are no external things to forces or interactions to bring it to an excited state. So in its rested state, it's called the ground state, or ground level. The electrons or the electron stability diminishes with increased higher energy levels. Why would that be? Why would the electron or the atom stability diminish with increased energy levels? Well, as you increase in energy levels, you're having to get further and further from the nucleus, and so you have a diminishing electron nucleus attraction. Okay, so we want to talk about atomic orbitals. And so there's 4 types of orbitals. First, there's the s orbital. It's spherical. The nucleus is at the center, at the intercept between x, y, and z axes, and the probability function is a perfect sphere around that point in space, being the nucleus. Then we have p orbitals. P orbitals are kind of dumbbell shape, or a figure 8, if you would. Then we have d orbitals, which look cloverleaf-ish. Okay, so what do you see here? You see on the s, you see 1 domain, and the p's, you see what? 2 domains along a given axis. And in the D's, you have 4 domains, 4 domains around that around the nucleus. And so 1, 2, and 4, easy enough to conceptualize. The final orbital type is the f orbital, and we're not going to even go there. That would be the lanthanides and the actinides, and we're not going to be dealing with those, so you don't need to worry about them. But just to describe the types of atomic orbitals is the s, p, and d is what we're going to be looking at. So we're going to look at the Schrodinger wave equation, where we have, for each electron, we have an energy level, we have a shape of an orbital, we have an orientation of an orbital, and given that 2 electrons can occupy an orbital, we have a spin. So I'm going to put some perspectives, or 4 different ways to describe atoms based on Schrodinger's wave equation. I want you to get used to, and this is an introductory slide for the description of types of electrons. We can think of electrons as shell electrons. We can think of electrons as subshell electrons. We can think of electrons in orbitals. Or we can think of the electrons in the electron spin with electrons within an orbital. And so shell electrons, subshell electrons, orbital electrons, and spin are 4 things that I'm going to describe coming up. But I wanted you to see these terms before we started describing what they were. Based on Schrodinger's equation, We say shell electrons are those that have the same value of n. And so if you look at the second quantum shell, the S block, and you go to the right over to the P block, those would all have the same value of n. That'd be 2s and 2p. They would have the same value of n. That would be 2. Subshell electrons are those with the same value of n and l. Okay, and so if they have the same value of n and l, that means they're within either a particular block. They're in a S block or they're in a P block, which describes different orbitals and shapes. Then you have orbital electrons. Those have the same value of n, l, and m sub l. Okay, and then you have how many electrons can an orbital hold? Only 2. And so if n, l, and m sub l are fixed, then m sub s, which is the fourth level, can either be plus 1/2 or minus 1/2. Again, this plus and this minus has no arithmetic value whatsoever. It's just a designator because we're using all the other whole numbers. And so looking at Schrodinger's wave equation, where n, l, m sub l, you can have a plus 1/2 for one electron, or if you have 2 electrons, one of them will be plus 1/2 and the other would be minus 1/2, but they would be orbital electrons and they would have the same value of n, l, and m sub l, but they're occupying the same orbital, so they have different spin. And so an orbital can hold no more than 2 electrons. Remember that. That is important at the atomic level as well as at the molecular level. So if an orbital does contain 2 electrons, they remain mutually distant from one another due to the electrostatic repulsion and opposite spin. So quantum orbitals and electron orbitals. Let's look at that. If the s orbital L is equal to 0. So if we're looking at s orbitals, L is equal to 0. There is 1 s orbital per quantum shell. So if you look at the periodic table, open up your book to the front cover and go down just the S block, you see hydrogen, and then below that you see additional elements. Okay, so for every orbital or every quantum shell, there is 1 s orbital per quantum level. Where n is equal to 1, then the s orbital is the only orbital at this quantum level, and that is closest to the nucleus. Each of the 7 quantum shells has its own spherical s orbital that radiates outwards with increasing distance from the nucleus. And so we're looking at the s orbital where L equals 0. There is 1 s orbital per quantum shell, and so here's the 1s orbital, and you can see it's spherical around the intersection of the XYZ axis. And this is s equals 2. It's bigger and further away from the nucleus, which is at the intersect. And this would be what? S is equal to 3. Okay, so they all have the same shape, but they have occupied different space because they are in differing energy levels. So this is the lowest energy level, closest to the nucleus. Get further from the nucleus at the second S, and 3s, so on and so forth. All right, where n is equal to 2, we have possible values of L, or shape, or 0, which is S, or 1, which is the p orbital. So for L equals 0, we have the 2s orbital. And for L equals 1, we have the 2p orbitals. Okay, so look at your periodic table, follow along. And so we have how many axes in a 3-dimensional model? We have an x-axis, a y-axis, and a z-axis. Okay, and what's at the intercept, or the intersection, I should say? Okay, that would be the nucleus. And so, and it's a 3-dimensional entity. So we have px, py, and pz. Would you agree that they all have the same shape? Yes, they do. How about that? And so they all have L equals 1 for the p orbitals. They all have the same shape. All right, and so there's px, Py, and Pz. All right. So for Px, Py, and Pz, m sub L denotes the relative orientation of each of the p orbitals. Okay, so m sub L could be 0 here, it'd be a -1 over here, and a +1 over here. Okay, and so that denotes the orientation of each orbital. That they all look the same in shape, but they all have different orientations, and that's described by m sub L. Okay, and so m sub L, if you look at Py, for instance, we'll call it 0, and we'll call the Px -1 and the Pz a +1. Again, the signs of negative and positive have no arithmetic value whatsoever. We're just using numbers, and we're using signs of numbers to indicate markers. They're basically designators. They have no arithmetic value. But everything is about if you look at a number line, everything is around 0, going left to the 0 or right to the 0 in whole numbers. So let's go to 3p orbitals. Okay, so one is along the x-axis, one is along the y-axis, and one is along the z-axis. That's m sub L. That's the orientation. Okay, so there are no d orbitals or f orbitals in the second quantum shell. Okay, and so what are the possible values for L in the second quantum shell? It could be 1 or 0. 0 would be for S, and 1 would be for P. Okay, so looking at the aggregate of the Px, Py, and Pz, you can see in this graphic the Px here, the Py there, and the Pz there. If you put them all together, that three-dimensional entity is what it would look like. And so where n is equal to 2, L is equal to 1 for p orbitals, we have Px, Py, Pz, and m sub L can be -1, 0, and +1. Each m sub L designates orientation, different orientations. They have no arithmetic value, they're just designators for orientation. Looking at the quantum orbitals and electron orbitals for n equals 3, where n is equal to 3, you can have an L of 0, an L of 1, or an L of 2. Where L equals 0, that's the 3s orbital. We're looking at the third energy level, third quantum level, and so we have each quantum level has an s orbital, so L equals 0 for the 3s. For L equals 1, it's the 3p's, Px, Py, and Pz. M sub L would be -1, 0, and +1 for m sub L, indicating different orientations but same orbital shape. And for L equals 2, we have the d orbitals, and that's what we see over here on the left. We have dxy. Notice they're all cloverleaf with the exception of the dz squared. Okay, so think of the d orbitals as cloverleaf. All right, and so where L equals 2, those are d orbitals. So we have dx squared minus y squared. That would be this guy over here. And dz squared. I wanted to talk to you about both of those. The dx squared minus y squared, notice that they're cloverleaf. And so this is one orbital, guys. This probability function lies along the x and y axis in the xy plane. Okay? And so x squared minus y squared is along the axes. dz squared is along the z-axis with this little donut configuration. Don't worry a lot about it. It's just an arithmetic probability function. And so just remember that dz squared is along the z-axis. So now, because electrons can now occupy the same space, if we have all the axes covered, x, y, and z, then we have 3 other orbitals to account for. And how can you possibly get 3 orbitals within this xyz domain that are non-intersecting? Well, you can look at the planes. And so we have the dyz. Okay, so that's the yz plane, and that cloverleaf lies along the dyz plane. We have the dxz plane, which is orthogonal or perpendicular to the yz. Again, cloverleaf. And what do you see about these? What do you note about those orbitals? They are non-intersecting with the axes, which means they're not touching base. They're not close to or even sharing the same space with the y squared, x squared minus y squared is z squared. These guys are all in the non-axis domains along a plane. And so dyz, dxz, and dxy. xy, of course, would lie along the xy plane. And so you would have a m sub l. So let's look at m sub l. We'll just put them like, it doesn't matter which one is which. I just use x4. You can mix them up any way you want, but m sub l has to be 0. And for 5 orbitals, because p's are 3 orbitals, m sub for d you got 5, and so an m sub l of 0, a -1, a -2, or m sub l of +1 or +2. And again, the positive and negative signs have no arithmetic value whatsoever. They're just spatial orientations. And so there are no f orbitals in the third quantum shell. And so what do you see? We see an s orbital for the first quantum shell, 2 shells in the second quantum shell, s and p, third quantum shell, s, p, and d, which is what we're describing here. And what quantum shell do you think f orbitals would show up? Well, they'd show up on the fourth quantum shell as we're building up. And so here's a 3-dimensional aggregate of all those d orbitals. And you can see that based on the coloring of each of the orbitals that they're non-intersecting. As always, the orbitals are positioned to give maximum distance between themselves and other orbitals. What we're going to do on this slide is try to relate orbital to L and m sub L and quantum shells and energy. And so you can see for n equals 1, if you go to your periodic table, there's only the s orbital. L is equal to 0 and the orbital is s. M sub L would be 0. Go to the next shell, second quantum shell, energy, and now you have s and p, where L is equal to 0 again for s orbitals, and L is equal to 1 for the p orbitals. M sub L now would be 0, -1, and +1. Notice that when we went up a quantum shell, we also added a shell of orbitals. Going to n equals 3, we now have the d orbitals, where L is equal to 2 for d orbitals, and m sub L, coming right down the middle here, is 0, -1, -2, +1, and +2. Let's go to the fourth quantum shell. This is where we enter into the f orbitals. And the L for f would be 3, and the orbital again is f. Fourth quantum shell is where the f orbitals begin. And so you'll notice that if you look at the pattern, it's 1, 3, 5, and 7. Okay, so odd numbers starting at 1. And m sub L for the d orbitals would be 0, -1, -2, -3, and +1, +2, and +3. What we're going to look at in this slide is principal shells and subshells. Try to get our head around that along with L and quantum shell 1 through 3. So to begin, let's look at the quantum shells. Those are the energy shells. Okay. On the left here you see shells. Okay. On the bottom here you see subshells. Okay. So the subshells would be L is equal to S, P, and D. Okay. And the shell electrons would be according to the quantum level that they where they exist. All right, so we're looking at quantum, the lowest energy going to highest energy. The lowest energy, of course, is closest to the nucleus, and so n is equal to 1. Let's look at the subshells. L is equal to 0 for S, L is equal to 1 for P, and again, L is equal to 2 for Ds. And each subshell is made up of 2L plus 1 orbitals. All right, so the odd number. All right, so L equals 0. Each quantum shell has an s orbital as you go on up or down the periodic table. So all quantum shells have an s orbital, L equals 0. If you look at the L equals 1 that's the p orbitals, and you will note that the p orbitals where L equals 1 began in the second quantum shell, okay, and they go up into the third quantum shell and the fourth and the fifth, and I think the sixth. I'd have to look at it. In any event, L is equal to 2 for the D. All right, now looking at what subshells exist in each quantum shell, where n is equal to 1, only the s orbital exists. It's only 2 electrons, or up to 2 electrons. Hydrogen would be 1, and helium would be the second electron. Go to the second quantum shell, and n equals 2, and that's where the subshells that exist in the second quantum shell are the S and the P. Those would each be a subshell, and they would have different shape designators, 0 and 1. And then go to the third quantum shell, and now we've added d orbitals. And so the electrons in the shell, the third shell, are S, P, and D. So what are the possible quantum numbers for the last or the outermost electron in chlorine? Okay, look at your periodic table. Chlorine is number 17, and so it has 17 electrons. Now each orbital can hold only 2 electrons, and so we will fill from the bottom up in terms of energy. And so the s orbital is lower in energy than the 2s, is lower in energy than the 2p, 3, 4, and 4, 3p and 4s accordingly. All right. And so our electron configuration for chlorine would be 1s2, 2s2, 2p6. Now, what noble gas has that electron configuration? All right. That would be neon. Okay. And beyond neon, you have the 3s and the 3p5s. That gives you your 17 electrons. And so that would be 2 plus 2 plus 6 plus 2 more plus 5 would be 17 electrons. And so doing the electron configuration, to answer the question, the last electron added is to the 3p orbital. And so n is equal to 3. L is equal to 1. Why is that? Because it's a p orbital. And what are the possible m sub l's for a p orbital? -1, 0, or +1. You don't know which one it is, but it could be any of those three. An m sub s could either be a +1/2 or a -1/2. Looking at the Schrodinger function for the second quantum shell, 2s, 2px, 2py, and 2pz, let's consider the following. The shell electrons have the same value of n. And so for all shell electrons, their n is the same. And so these guys are all shell electrons. The subshell electrons have the same values of n and l. And so the electrons that are subshells would be the 2s, and then another subshell in the second quantum level would be the 2p's. Okay, so those are the electrons with the same value of n and l. So all the electrons in these orbitals are subshell electrons. All right. The only time we would call them shell electrons is in consideration of the s. Likewise, the s is the subshell in of itself for the second quantum shell, as is the p orbitals are a subshell in the second quantum level. Orbitals, electrons with the same value of n, l, and m sub l. Okay, so orbital electrons have the same value of n, because they're in the same orbital, they have to have the same value of n. L, because they're in the same orbital, they certainly have the same shape. And m sub l, their m sub l's will be different for the d orbitals or p orbitals. You don't know which ones they're going to be. And so these are the orbital electrons. The 2s are orbital electrons. The 2px are orbital electrons. The 2py are orbital electrons. And the 2pz are orbital electrons. You don't know which is which, but if there are 3 electrons, then there'll be 1 in each of these subshells, or orbital electrons, I should say. All right. Okay, let's ask ourselves, what are the possible quantum numbers for 2p electrons? Well, the p electrons, of course, there's 3 different orbitals, px, py, and pz. So what are the possible quantum numbers for them? Well, it's 2p, and so the energy level is 2, n is equal to 2. Because it's a p orbital, L is equal to 1. And so there's 3 orbitals. So m sub L, if L equals 1, then m sub L can be either a -1, a 0, or a +1. Let's ask the same question for the 3D electrons. What are the possible quantum numbers for 3D electrons? Well, there's your 3D electrons. Z squared, xy, yz, yx, and x squared minus y squared. It doesn't matter which order you arrange them, just as long as you have all 5 represented. Okay, so we're in the 3rd quantum shell. So n is equal to 3. D is equal to, L is equal to 2. And there are, if L is equal to 2, then m sub L can be equal to -2, a -1, 0, +1, or +2. Looking at energy of orbitals in a single electron atom. A single electron atom would be hydrogen, of course, or maybe helium if it lost one of its valence, or if it lost its electron, one of its 2 electrons. Okay, so energy orbitals for a single electron atom are energy degenerate, meaning that they all have the same energy. The energy depends only on the principal quantum number n. And so which of these quantum shells does the energy, where's the energy lowest? Well, it's down here, of course, the 1s. And so the energy of that electron, if it's down here, would be the Rydberg constant times, well, this quantity would be 1, because square of 1 into 1. In any event, it would be equal to the Rydberg constant, negative quantity there too. And where would you find that electron? Right down here. That said, if hydrogen atom is in the excited state, meaning a non-ground state, that electron may be found in anywhere in the 2nd quantum shell, or anywhere in the 3rd quantum shell, 4th quantum shell, so on and so forth, depending on what the external energy boost was. And so you go from lower energy to higher energy, and an energy degenerate according to quantum shells. All right. So n is equal to 1, n is equal to 2, n is equal to 3, 4, and so on. But in the ground state, you're going to find that puppy right down here at the lowest energy. Energy orbitals of multi-electron atoms are different than for the single atom. You can see that the energy depends on both n and l, and you can see that where they are non-degenerate in the 2nd quantum shell, certainly non-degenerate in the 3rd quantum shell, so on and so forth. So let's look at multi-electron atoms. where n is equal to 1, L is equal to 0, meaning an s orbital. And n being what? The lowest energy. See, our energy is going from bottom to top. The second is n is equal to 2, because we're in the second quantum shell, and L is still equal to 0 because it's an s orbital. This one, of course, would be still n equals 2 because we're in the second quantum shell, and then L equals 1 because it's a p orbital, and the subshell is p. And so the second quantum shell has two subshells, has the s and the two p's. The next is, of course, the third quantum shell. L again is 0 because it's an s orbital. And like the predecessor, in the second quantum shell, the 3p orbitals are non-degenerate with the 3s, and n is equal to 3 and L is equal to 1 because it's a p orbital. And then finally, let's go ahead and look at where L is equal to 2 in the third quantum shell, because those are 5d orbitals. Okay, and so you can see the lesson here is that multi-electron atoms are non-degenerate in their electron energy levels. Let's look at the Aufbau principle and take that into consideration where we were just looking at the non-degenerate energy levels. So for a multi-electron atom, the Aufbau principle states that electrons fill lower energy atomic orbitals before filling higher atomic energy orbitals. And that's Aufbau is German for building up. So some important attributes of the Aufbau principle are that by following this rule, going from bottom to top, energy-wise, we can predict the electron configurations for atoms or ions. That's very important. Secondly, we can, through this process, gain knowledge about the ground state electron configuration of elements in their ground state. That's just their lowest energy state. And it also enables us to predict the properties of elements based on their electron configuration. And it explains why the periodic table works so very well. And so the Aufbau principle, again, to restate it, electrons fill lower energy orbitals before filling higher energy levels. Hund's rule states that the most stable arrangement of electrons in subshells is the one with the greatest number of parallel spins. And what parallel spins mean is all the electrons are either simultaneously plus 1/2 or simultaneously minus 1/2 in the m sub L, the m sub s quantum number. And so let's look at carbon, where three possibilities exist for the 2p2 ground state electrons. The first is px, py, pz, of course, and we have two electrons that are both occupying a single orbital. In the second one, we have two electrons occupying individual orbitals, and in the third one, we have two electrons also occupying individual orbitals. These are on the left called spin-paired antiparallel. Spin-paired means that they are in the same orbital, and antiparallel means that one is going in one direction, let's call that plus 1/2, and the other is going in the minus direction, let's call that minus 1/2. But those don't fit the Aufbau, the Hund's rule. Looking at the second example, you can see that they are occupying different orbitals, as they should, but they are not spin parallel, they're spin antiparallel because they're going in opposite directions. And on the final one, you can see that it does comply with Hund's rule, where the electrons are spin paralleled and occupy individual atomic orbitals. So let's fill up electrons in the lowest energy levels using the Aufbau principle. Looking at the hydrogen atom, we have one electron. For hydrogen, just one electron. And so we'll put that puppy right down there in the 1s orbital because that's where it's most stable. It's closest to the nucleus, and the electrostatic charge between positive and negative is greatest. And so this here would be what we call an orbital diagram, and this over here is a notation diagram. Let's look at helium. Helium has 2 electrons because its atomic number is 2. And where do you think that second electron will go? Well, of course, it'll go into the lowest quantum shell using the Aufbau principle. And you can see that they're spin anti-parallel. That follows the Hund's rule. Then let's go to there's this is the atomic orbital representation diagram, and this is the noted notation that we use for electron configurations. Going to this lithium, the third, we have now another electron, and where will it go? It'll go in the 2s. And looking at so there's our electron configuration for lithium. It's 1s2. These would be these guys down here, and 2s1 be this guy over here. Looking at beryllium, which has 4 electrons, using the Aufbau principle, where will the fourth one go? It'll go into the 2s. And there's spin anti-parallel again, and so it has spin anti-parallel, spin anti-parallel. These electrons are furthest from the nucleus, and they would be the valence electrons. These guys down here are the core electrons, and they're not going to be used in bonding. So if beryllium reacts, it's going to use those 2s, those two 2s orbital electrons. Going on over to boron, the 5th electron, using the Aufbau principle, will go into the 2p orbital. And looking at, there it is. So the electron configuration for boron would be 1s2, that'd be these guys. 2s2, that'd be these guys, and 2p1, that'd be this one right here. And let's look at carbon. Let's add our next electron, and let's see where it's going to go. Is that right? No, it's not correct, because it's violating Hund's rule. And so how about that one? Yep, that one is compliant with both Aufbau and Hund. Hund would be of course, spin anti-parallel in the same subshell, or spin parallel in the same subshell. Okay, so again, Hund's rule states the most stable arrangement of atoms in subshells, and that's what this is. This is a single subshell in the second quantum level. Is the one that's most stable with the greatest number of parallel spins, and so this indeed gives us the greatest number of parallel spins according to Hund's rule. And its electron configuration would be 1s2, 2s2, 2p2, where these electrons, following Hund's rule, are spin paralleled and occupy the greatest number of orbitals. Nitrogen was going to go into the pz orbital. All right, and so electron configuration is shown to you there. Let's look at oxygen. We're going to add an electron now. Each of these 2p orbitals, there's 3 of them, has a single electron, but now we have to add an extra electron. So it's going to go in any one of them. By convention, we'll just represent it in the first one. So it'll be a spin paired anti-parallel for the second electron. And when we get into Lewis structures, oxygen has 2 lone pair electrons in its valence shell, and so there'll be these guys and these guys, and these 2 electrons will be used in chemical bonding because they're unpaired. And so the electron configuration for ground state atomic oxygen is 1s2, 2s2, 2p4. Looking at fluorine, we'll add another electron just like we did. So it's spin paired anti-parallel. Has 1 valence electron that's used, even though it has 3 lone pair of valence electrons. Those will never be used for fluorine especially. Just this one electron will be used, so it'll only have one bonding partner. Okay, its electron configuration is shown to you there as 2p5. We'll round it out with the noble gas neon, and neon, of course, now has a complete octet. And you're going to hear a lot about a complete octet in the second quantum shell, where all electrons, all valence electrons, are their orbitals are filled, and it's quite stable and fairly unreactive because there are no single unpaired electrons. And so neon's electron configuration is 1s2, 2s2, 2p6. Keep this in mind as we go from neon down to argon and the periodic table, so on and so forth. We're going to still have this s2 p6 arrangement with the valence electrons in noble gases. Looking at multi-electron atoms, of course, Schrodinger's equation was for only one electron, and it does not take into consideration electron-electron repulsion. Because electrons are of like sign, they're going to repel each other, and so we have core electrons and we have valence electrons. And multi-electrons have two types of electrons. Core electrons, those that are closest to the nucleus, are not used in chemical bonding. And we have valence electrons, those that are furthest from the nucleus, and those are used in chemical bonding. So only the valence electrons are used in chemical bonding. Do not use core electrons. It's not going to happen because they're in probably in the p construct. They're going to be filled. Okay, looking at radial probability distributions. There's a lot of information on this slide. So you see a curve here and a curve here and here, and down here, so on and so forth. The x-axis discusses or illustrates electron density as a function of distance from the nucleus. And so the radial probability distributions above, they give us an idea about the electron density at a radial distance from the nucleus, which is defined as the x-axis. It's defined in the y-axis in each of the above curves. Okay, and so looking at the 1s orbital, where n is equal to 1 and L is equal to 0, you can see that the electron density map shows a radial probability fairly close to the nucleus. And we won't worry about what these units are. Just keep in mind relative distances as we go. The second one, you can see we're at n is equal to 2, and we have the 2s, so this would be the radial probability of the 2s electrons, and you can see that its maximum probability is further away from the nucleus than the 1s orbital. Okay, and we'll go to the third one, and the third one says n equal 2, okay, L equals 1, that's going to be a p orbital, so the two p orbitals have approximately the same distance as the 2s from the nucleus. Going down here to the third quantum shell, we have our s again, and so in the second quantum shell, the maximum for the radial probability for the 1s was, something around what looks like 1.5, 2. The 2s, the maximum just a little bit above 5, and the 3s, the maximum is, around 13, 14, somewhere in there. And so you can see that the radial probability, as the quantum shells get higher and higher, the distance from the nucleus increases. Looking at the p orbital, 3p orbital, orbitals, I should say, the subshell, you can see that their radial probability is roughly approximately equal to the s in the third quantum shell in terms of the distance from the nucleus. And finally, looking at the d orbitals, you can see again we have a d orbital construct which isn't terribly different than the P and the S for that quantum shell. And so where N is the principal quantum number and L is the azimuthal quantum number, that gives us the orbital shape, of course, S, P, and D. And so we're looking at L equals 0 for S, L equals 1 for P, and L equals 2 for D. And so the inner shell electrons effectively shield the outer shell electrons from the nucleus, thereby reducing their attraction to the nucleus and increasing their relative energy. And that's important. This is called core shell valence shell electron pair repulsion. In multi-electron atoms, the attractive force of the nucleus for a given electron increases as the nuclear charge increases. Okay, and so we're going from left to right, the periodic table. And when that happens, the density of positive charge, we can say, let's look at boron, has 5 protons in its nucleus, second quantum shell. Carbon has 6 electrons in its nucleus, and so carbon has a greater density of positive charge in its nucleus than does boron. Go over to nitrogen, look at your periodic table here, go over to nitrogen from carbon, and again you have atomic number of 7, and now we have 7 protons in the nucleus, and again the positive charge, effective positive charge, we're going to call it effective nuclear charge here in a little bit. But anyway, the effective positive charge in nitrogen is greater than that of carbon because you're adding increasing number of protons in the same quantum shell. And so we'll call this effective nuclear charge in chapter 9, but you should just be aware of it. Let's look at electron configurations in atomic orbitals. And to summarize, the Aufbau principle says that the electrons occupy orbitals in a way that minimizes the energy of the atom. Hund's rule says that when orbitals of identical energy, degenerate orbitals, are available, electrons initially occupy these orbitals singly, and with the spins parallel. Pauli, which we haven't talked about until now, says that no 2 electrons can have all 4 quantum numbers alike, and so that means that any orbital that is fully occupied, the spins have to be spin paired and anti-parallel for the Pauli exclusion principle. And so the way we fill these up, looking at the quantum levels and atomic orbitals, excuse me. The first quantum shell has only S, and let's look at that. And the second quantum shell has S and P. So L is equal to 0 for S, and L is equal to 1 for the P. And you can see there's the third quantum shell. And notice that as we go up in energy from first to second, we add yet another set of subshells, another subshell. Same holds for the third quantum shell, S, P, and D. L is equal to what? 2 for D, yes. 1 for P and 0 for S. And so we're in a third quantum shell here. And now the third quantum shell has both S, P, and D. As shown here, they're all shell electrons, but we have 3 different subshells. That'd be the 3s, the 3p, and the 3d. And let's add another quantum shell. What are we going to do when we do that? That puppy right there, the 4f. So the fourth quantum level has all 4 s, p, d, and f, as shown here in the red box. So these guys are all shell electrons, and how many different subshell electrons do they have? They have 4 different sets of subshell electrons. 5 looks just like 4, and then as we start to go up again in energy away from the nucleus, we have the 6th quantum shell, where we drop off the f orbitals. Look at the bottom of your periodic table right now. In the bottom, you will see the lanthanides and the actinides, and the lanthanides are the 4f subshell, and the actinides are the 5f. Okay, and so we're starting to run out of orbitals here. So the 6s, we have three subshells, 6s, 6p, and 6d. And then finally we have the 7th quantum shell where we run out of electrons and protons, basically, and we have only two subshells, 7s and 7p. The quantum levels and atomic orbitals, looking at that. Okay, so how do we fill these things? How do we write electron configurations? Well, you'll notice that we talked about the octet, especially in the P block. Anytime we have a filled octet, that would be S2 and P6. That's a noble gas configuration if you look at your periodic table. And so all 7 quantum shells have an s orbital, and when it's filled, that is filled with 2 electrons. When the p orbitals have 6 electrons, they have 3 orbitals, and how many electrons can an orbital hold? 2. Therefore, we have 6 electrons possible in each of the quantum shells for the p orbitals. Notice that the p starts in the 2nd quantum shell. And we have the d orbitals, which have 5 orbitals, and each orbital can hold 2 electrons. So we have 10 possible electrons in the 3rd quantum shell, 3D, I should say, 4D as well, 5D as well, and 6D as well. And so if you go to the transition metal block on your periodic table, which it goes, the first set of d orbitals you see on the first and the 3rd quantum shell are the 3ds. Then you go down, look at the periodic table, 4ds, 5ds, and 6ds. And so you only have 4 subshells, or you have 4 quantum levels really represented in the d orbital construct. And then going to lanthanides and actinides, you have 2. Okay, so 1 orbital for each subshell. And 3 orbitals for the p's, and 5 orbitals for the d's, and then 7 orbitals for the f's. So 1, 3, 5, and 7, odd numbers starting at 1. Looking at electron configurations and how the electrons are distributed among the various atomic orbitals in an atom, we see that the 1s1, that's our abbreviated form, it's called the principal quantum number is n, and so that number right there represents the energy level for that quantum shell, which means it is the closest to the nucleus. That first quantum shell is closest to the nucleus. This has an s orbital where L is equal to 0, and it only has 1 electron, so what atom would that be? That would be hydrogen. This is the angular momentum quantum number. Don't forget it. We talk about angular momentum quantum number. It's L. What does it describe? What does L describe? Anybody remember? It describes the shape. Okay? And so this describes the energy level, and this describes the shape, which is spherical. The 1 superscript is the number of electrons in the orbital or subshell. And so the orbital diagram for hydrogen looks like this. This is the orbital diagram, and this would be electron configuration diagram. Okay, so the order of filling subshells, let's go to the, and I represent them just like in the previous slide, 1s, 2s, 2p, so on and so forth. And so you fill the 1s first, and that's only going to take 2 electrons. So the first quantum shell can only have 2 electrons in it. When it has 1, it's hydrogen. When it has 2, it's helium. And don't forget, S can hold 2 electrons. And so the next orbital we're going to so this slide basically shows you how it works. We fill up the 1s first, then we go all the way to the back and fill up the 2s. Then we go all the way to the back, and then we start filling 2p, and when that gets filled up, we fill up 3s and go all the way in the back, and then we start filling the 3p's, and when the p's get all filled up, then we go to 4s and start filling those guys. And so it's just this big zigzag, and that would be the order in which electron orbitals are filled. or atomic orbitals are filled. So what is the electron configuration for magnesium? Well, it has 12 electrons. And so the orbitals that will be involved for magnesium, look on the periodic table. Where does magnesium sit in that periodic table? It sits in group 2. Okay, so its valence electrons will be an s orbital. And so it's so the energy levels, 1s is lower than 2s, which is lower than the 2p, which is lower than the 3s, if you look at the non-degenerate electron configuration. And so we can represent that with magnesium as 1s2, 2s2, 2p6. Here, this is a noble gas configuration for what? Neon. And there's the other two valence electrons. These are the valence electrons right here. So magnesium only has two valence electrons. What are the core electrons for magnesium? Right here, 1s2, 2s2, 2p6. And that's the neon electron configuration. And remember, the noble gas configuration is a very stable configuration for electrons. And so you will not be using the core electrons. You only use the valence electrons. So you add those numbers up in the surdscript and you get 12 electrons. We abbreviate that because this is neon, 1s2, 2s2, 2p6, that's neon. We can abbreviate this form with an abbreviated form. So we just show in square brackets neon, which is this electron configuration, with the valence electrons next to that, 3s2. Okay, and where neon is again equal to 1s2, 2s2, 2p6, we abbreviate it with neon in square brackets. Okay, let's represent electron configurations for carbon, which has 6 electrons. And we're going to use the SPDF notation, that's the condensed notation, where it's 1s2, 2s2, 2p6. The expanded notation, which we're not going to use very much, would be 1s2, 2s2, and we're looking at the in the ground state here, we have a pxy with 1 electron to 2py with 1 electron. So 2px with 1, 2py with 1 electron. That would be they would Hund's rule. They would also be they would all have the same spin. So these two guys will have the same spin in their most stable ground state. In the SPDF notation, the orbital diagram, so you should be able to look at this and get to this representation. And I use this quite a bit in this class, orbital diagrams. And I will use single-headed arrows rather than double-headed arrows. But anyway, you can see that this is for carbon, the core electrons are the 1s, and the valence electrons are the 2s and the 2p. And whose rule is this following? Where they're going in the same direction and occupying separate orbitals. That would be Hund's rule. Okay, so let's use the off-pop process looking at the transition metals. Looking at the first transition metal, that would be our buddy Okay, so we'll look at electron configurations in the periodic table according to blocks. And the S block is where these elements have their valence electrons and the s orbitals of the respective quantum levels. Here's the P block, which is the nonmetals. Typically, the valence electrons for nonmetals will include the preceding s orbital electrons in the same quantum shell. So, for instance, the quantum shell of 2 would have a subshell of 2s and a subshell of 2p. The D transition metals, the D block, the transition metals, those are all, everybody in the transition block, all the metals in the transition block have valence electrons in the D shells. Also, you should note that the preceding s orbitals for the transition metals are also valence electrons for transition metals. In fact, we're in the fourth quantum level here, we're in the third quantum level here. Fourth quantum level is a bit further out, so actually these electrons are used first in valence or in electron exchange, followed by the continued use of the d orbital electrons. Let's look at vanadium, for instance. Vanadium number group 5, number 23. It has 23 protons, 23 electrons. Its core electrons are over here in argon. And so argon would be your prefix for the vanadium. And in your S4s electrons and then 1, 2, 3, I believe we were talking about vanadium. So it'd be a 4s 3d3 would be your electron configuration for vanadium. Don't forget, chromium and copper are going to be unique in that they will take an electron from the preceding s orbital and put it into its to fill the d shell here and to fill the d shell in copper. And so f orbitals are down here, lanthanides and actinides. Their valence electrons are in the what we call the f block. We're not going to spend any time down here, so don't worry about those. But I should be able to give you a metal, say for instance 10, number 50. You should be able to write an electron configuration for that element. And how would you start that? Well, you'd start at the preceding noble gas, and then you work your way over to the metal of interest. Here's group 1, group 17, group 18, group 7 or 8 if you like. Here's how they represent the electron configurations. Notice they're always going back to the preceding noble gas and then doing the, for fluorine, for instance, would be 2s2, 2p5. Saying for what? Saying that for fluorine in the second quantum shell, its valence electrons would be the s orbital electrons, and 5, it's 5 2p electrons. And so you just write it out that way. Your authors like to use, sometimes they'll intermix them, but 4F14, 5D10, 6S2, and 6P5 would be the electron configuration for antimony. So there you are. We have completed the lecture for Chapter 8. Be ready for the next one. Talk to you later.